So we were looking at this. We're looking at various problems. What were we doing? Okay, I'll give a bit of a broad picture, and then we'll do an exam question because there's space.
First John was speaking.
Yeah. No. So what is a computational? Okay, so what is a decision problem?
That's what we're doing.
Decision problem is a computational problem, and the computational problem comes with the description of what the input has to be like, okay, and what the question is about this particular input. The input could be a graph, or a number, or something, or a map, or whatnot, okay, or an integer programming problem. That's an example. Now. And so these are computational problems, and a special class of computational problems are called decision problems, and that's where the question is a yes/no question. Mm-hmm. Okay. And that's what we're basing the theory on. Okay. Now, what we have is problems which are easy to solve in so yes/no question. And easy to solve, we defined as there exists or admits a polynomial-time algorithm. Okay, and we saw some examples, and one of them was shortest path, and another one was the dynamic programming. In some cases, the dynamic programming algorithms give you a polynomial-time algorithm, but not always. So, for example, the knapsack problem, it doesn't, because the number of different states is too large. Yeah. So if you can do a dynamic algorithm where the number of states is not very large, where the number of states is polynomial in the size of the problem, and then you should be all right. And it basically constitutes a reduction. So a reduction was kind of so a reduction. The formal definition is given somewhere there. I'll look it up and know it in case you need to say it. But informally, one can think of intuitively a reduction as I have an algorithm that solves a particular problem, okay, and I have a different problem. Now, is there a way to use that algorithm that solves problem B or solves problem A? Mm-hmm. And that way, how you can solve problem B, problem A using the box of problem B is called a reduction, where you reduce A to B.
Yeah.
Okay. Yes. Now, this means that the reduction is polynomial time as well. So somehow. Can be done in an efficient way. Yeah. So not the knapsack problem. There you're doing a reduction, but it's exponential time or exponential size, whatever. So this is the basic idea. Then there's the idea of the class NP. Okay? And the class NP is this is so easy to solve. So this is the class P problems. NP is it stands for non-deterministic polynomial.
Non-deterministic is the first word. Oh, because it's non. Yeah. Like instead, every time I've seen it, it's no dash. It's just one word. Yeah. Dash.
Okay, so that's the first time with that. And there are several ways how to think about it, but we said that these are the problems, decision problems, where you don't know whether you have a polynomial time algorithm to solve it. You might have. If you have, then that's already in it. But definitely what you have is you can easily check whether the answer is yes with not much extra information. So it goes to the yes answer can be verified in polynomial time using extra information bounded by polynomial time. So another way how to think about it is it's problems that can be solved in polynomial time if you have infinite parallelism.
Parallelism.
Yeah. So you know today's computers have typically there are several what I call cores, so they can execute. So this one has 2, I think, and my new one has 4, so it can do 4 things at the same time. CPU. But if you have, so that doesn't help. But if there was an infinite number of cores, that would solve these problems in polynomial time. Okay? So it's kind of like now you have to make a decision which of these things to do, or you could say do them all once, okay? And then you can kind of thread infinitely. So in a way, when you think about an example of what was the problem? The knapsack problem. Okay. So for example, the knapsack problem, you can think of it as okay. So you take the first item. Now you have to decide whether you take it or not. Okay. So you just thread the program. So you create one thread, which is checking what's going to happen if I take it, and another thread, which is checking what's going to happen if I don't take it. And ask them what is the best. So ask the first one, what is the best optimal solution? If I take it, what is the best optimal solution if I don't take it? And it continues, and it says, well, now I've got, again, now I've 2 options for the, 2 options for the second item. So take it or not, take it or not, okay? And you can branch it like this. And of course, if you're doing if you only can do one thing at a time, you have to do all these branches one after another. And that gives you an exponential, because there are an exponential number of these branches in the end. That gives you an inefficient algorithm. But if you could do them all at once, an unlimited number of them, then you could solve it in polynomial time, because just, you know. So that's another way of thinking about it, and that's so that's where it comes from. Non-deterministic. It's not that it's not doing them in parallel, but you can say that, oh, it's going to be this or that, but I'm not determining which one it is, but I'm just giving you a kind of an algorithm that will run in polynomial time if at every point in time it knew which is the right branch. Well, it doesn't know it, so yeah. Okay. So that's the idea of NP, and now depending on your point of view, NP is either easy problems or hard problems. Okay. So in the very grand scheme of things, these are all the decision problems. Okay. And at the top there is a large slice of undecidable problems. There's no algorithm whatsoever for them. No computer that can solve them. Can be proved mathematically that some problems can't be solved. But one of them is, if I give you a MATLAB code, is it going to stop? No, that's the problem. Okay, so the input is a MATLAB code. The question is it going to stop? And some input, MATLAB code, and some input for the code. And the question is it going to stop? So there is no algorithm that would be able to decide, for no matter what code, whether it's going to stop or not. That's an example of an undecidable problem. And then there are some hard problems that are probably not polynomial time. And then somewhere like at the bottom, so it depends on your zoom. So this is really huge, right? This is really, really huge. But depending on your zoom, then at the bottom, there's the class NP. And at the bottom of the class NP, there's the class P. So these are the polynomial time solvable. So every polynomial time solvable is in NP. Because, well, if it can be done non-deterministic, if it can be done polynomially without branching at all, then that already is subsumed in the definition of doing it with branching. So the branching is just one branch every time. Okay. So and if yes is the answer, it can be verified in polynomial time using no extra information, because the polynomial time algorithm for the problem is also the verifier. So that's the kind of idea. So P is definitely a subset of NP. Whatever is in P is in NP as well. But whether P is equal to NP is unknown. So that's what we said. And what we have is that somewhere at the top, here are the NP complete problems. And there somewhere you might have non-deterministic log space and log space and circuits and things that really easy to solve. So it's a huge landscape of complexity classes. Look it up. There's a Wikipedia of complexity classes. And all of them are described there. And so what we think, and for our applications-based approach, this theory, really what it's telling us that these are good. Okay. And in practice can usually be solved all right. These are bad. So need some tricks.
Okay.
And we can we probably want to, we won't really be chasing the optimal solution if we're doing some kind of optimization. Because it's out of reach most of the time. These ones, nobody knows whether, well, they are really. So. But and that's the idea. Okay. But maybe if P is equal to NP, then this whole thing maps to one. So P will actually be of P, and NP complete won't have any meaning because the whole of P will be NP complete. So that is a possibility, a distinct one, but well, no one's proved whether it looks like this or whether it looks like.
Going into
for practical purposes, because nobody knows a polynomial time algorithm for any of these problems, we're assuming that it looks like this. Yeah.
I just want to say that with P being P belonging to NP in the context you put it in there again.
Yes, it's a subset. Not
subset, yeah. Meaning in group theory.
Yes.
Can we actually make that statement at the bottom that you made, P is equal to NP, by proving something as a subset? Whereas if it's cyclic or if it's what's the other one I'm thinking of? Drawing a blank. Abelian. if you can say that P is a subset of NP,
yes,
in group theory, let's say.
Yes. You can also say that something is a subset, that's quite a general.
But can we make the statement that P is then equal to NP?
When?
If it makes up the group, isn't it?
Let's leave it for later.
Leave it for
later. Because probably not everyone here is interested in that. We can talk about it later, but okay. So that's the idea. Now what we try to kind of learn is to say a couple of things that we know are here in polynomial time, and we've had some examples. Right? So sorts of stuff. Practically all the examples that the graph algorithms that Philip showed you. Mm-hmm. Yeah. So some polynomial time examples. there are problems he didn't do, which are the NP-hard problems in graphs. So some polynomial time. So the problem and the algorithm, I think you had shortest path. Okay, and that was Dijkstra. Yeah, Dijkstra's algorithm. I always keep forgetting these names. There was the minimum spanning tree. Do you remember that one? There were several, so for example, Kruskal's. And there's also, yeah, better algorithms than Kruskal. There was another problem, which was the maximum flow, which is the Edmonds path algorithm with improving paths.
BOR.
It's a U with a ring.
Oh. Max flow.
LP.
Linear program. What?
No. So there are algorithms we didn't see, like interior plane. It's called ellipsoid. There are two different algorithms that are polynomial time. Simplex, we don't know.
Yeah.
Depending on how you choose your pivot elements, nobody has found a version that will be provably polynomial time. Okay, and then we had some hard, so NP hard, NP complete. We haven't seen so many of them, but one of them was knapsack, well, SAT, we said. That's the satisfiability problem.
Oh, right.
You get a formula, it's satisfiable. Knapsack in general. Okay. And the one that we still need to do is integer linear programming.
Yeah.
And that is so, and that is what really remains, is to prove that integer linear programming is NP complete. So exercise. Show that ILP feasibility is NP complete. So what is ILP feasibility? We want it to be a decision problem, something to do with integer programming. Okay, so the input is, well, let's say it's a.
No, it's fine.
So let's say you have an n by n matrix A with integer entries.
Yep.
And an m vector of integers B.
Yeah. Then we have a C.
And then we have a question. Which is, does there exist Something like this.
I don't know if I'm going to say the word correctly, but whenever you do an ILP in the simplex method, it's always subject to division, so therefore it could lose its integrality. Say that word correctly.
Yes. So you should remember last year then.
It's in the report.
So what we were doing last year was 2 different algorithms for integer programming. Do you remember? Do you recall any one of them? No? Come on. You knew them for the exam a year ago.
There was the drunken assessor.
No.
No, but that didn't need to be integer. No,
There was a branch and bound algorithm.
Branch and bound. Oh yeah, that had to stay as integer. That was one of the last ones.
And there was a cutting planes algorithm.
Oh yeah.
So that used linear programming as some sort of a sub-routine. Okay, this is basically, the question is really whether this integer program is feasible, has a feasible solution. Now, if you want to optimize, you can turn this into if you could solve this problem, you could turn it into an optimization engine where you add another constraint asking whether the objective function is less than or equal to 200, or greater than or equal to 200 or something. But you can do greater than or equal to by multiplying by -1. You can do non-negativity using this as well, and you can do everything. But this is a generic way of doing it. Yeah. So that's the problem. What we want to show is that it's NP-complete. So showing that something is NP-complete has 2 parts. And the first part is it's in NP. So that's the part where it's saying it's not too hard. Okay, so NP-complete means really, when you look at the picture again. Yeah.
Need some tricks.
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 Oh, yes.
Sorry, the brain.
No, yes.
The brain gets in the way.
So NP-complete is really just this list of slides here. So we have to show that it's not harder, it's not above.
Yeah.
And we have to show that it's hard within NP. So the first thing is that it's not too hard. It's in NP, and it being in NP, you said was it's easy to check that the answer is yes, and it is because if the answer is yes. Okay, it's not so hard. So maybe it's not so easy. It's actually not so easy. It actually takes about another 2 lectures or something. But okay.
Give us the short and sweet.
Then it can be shown that there is a feasible solution whose size is polynomial in terms of the input. Okay, and then when you have access to this feasible solution, you can check when you plug it in quite easily these calculations. The multiplication is obviously polynomial-time. Comparing it with the right-hand side is obviously polynomial-time as well. So that's okay. But it's not immediately obvious that the solution should be small. So it could be like, because well, I don't want to give it too much detail. It's just because. these things, so there could, so in theory, it can happen, but it could happen. So you need a bit of geometry of numbers and things. In theory, it could happen that you would have a very, very small description of things. So small and like, not that the numbers are not large, but the number of digits that you need to write is not very large. But then the actual solution would be a lot. Doesn't happen. Okay, and the more important bit that we're looking at is that it's NP-hard. And from the theory we did, it's enough to show that we can reduce some problem about which we know that is NP-hard to it. That is a theory. That if P is an NP-complete problem, and C is an NP, and if we can find a polynomial time reduction from the NP-complete one to the one that we're interested in, then the one we're interested in is also NP. So you should take some thing that we know is NP-complete and show that it can be solved using integer programming, and that will do. So one thing you could do probably is take the knapsack problem, say, oh, we know the knapsack problem is NP-complete. Okay, we didn't really prove that. Well, yeah, you could say. We didn't really prove that SAT is NP-complete either. But just to show you, it really is just to show you kind of the general method which is used to prove theoretical results like this. So what we're going to do is we'll take the SAT problem and we'll reduce it to IOP feasibility. Yeah? Okay, so what we need is an algorithm that takes an input to the SAT problem and spits out an input to the ILP feasibility problem. Okay. And so what is the input to the SAT problem? It's a CNF formula. Conjunctive normal form formula. Input to SAT, a CNF formula. Okay. Want input to ILP. So I won't write it in the matrix form. I'll write it just as constraints. So for each true false Boolean variable, what we call them? A, B, C.
Yeah, little.
I'll say A. Appearing in the formula, we have a binary decision variable. I'll call it XA not to confuse it with A. This is X. I need to start a new paper. Okay. And for each clause, we have a constraint So what is the clause like? clause is something like A or not B or C. Okay, the negations could be elsewhere. So from this we get XA plus. The negation is 1 minus XC.
Good, thanks.
Is greater than or equal to 1. And there are also constraints that are telling you this for each A. Now observe that phi is satisfiable if and only if this phi over P has a feasible solution. As you observed, is it clear? Not at all. You should get out of the way. Okay, if phi is satisfiable, that means we have true or false assignments to all these variables.
Yeah.
So that the whole formula is satisfied. That means every clause is satisfied because the formula is a conjunction of clauses. So every clause has to be satisfied. So when you get any clause you have, you know at least one of them is going to be true. So what you're going to do, you're going to put XA will be 1 if A is true in the formula. And XA will be 0 if A is false in the satisfying assignment of the formula. And so if one of them was satisfied, it means that either this is 1, A is 1, or B is 0, or C is 1 in this example. So if C is 1, true, A is true, or B is false, or C is true. Because the clause was satisfied. So at least one of them will have to happen. So if C is true, then this is 1. And whatever this is not negative, so the sum is going to be at least 1. If A is true, then this is 1, and whatever this is not negative, so the sum is going to be greater than or equal to 1. And if B is false, then this is 1. Whatever this is not negative, so the sum is going to be greater than or equal to 1. So every clause was satisfied means that this constraint will be satisfied. Okay? So if this is satisfiable, then we find a corresponding feasible solution. And conversely, it's the same thing. We have a feasible solution to this. So we have some values for these x's that all these constraints are satisfied. So is every clause satisfied? Well, so how could it happen? We have zeros and ones, and the sum of here is at least 1. So that means, because each of them is, so this is either 0 or 1. This bracket is either 0 or 1. This is either 0 or 1. Mm-hmm. And when you add them all together, you get 1. That means that at least that they can't all be 0. So if one of them is 1, and if one of them is 1, then you set this one to true. So going backwards. Whenever the XA is 1 for some A, you set A to true. And if it's 0, it's false, and you get satisfying assignment. So a satisfying assignment to the formula gives you a feasible solution, and conversely, a feasible solution gives you a satisfying assignment. Via this kind of true is 1, false is 0. Okay? So the answer is yes if and only if it's yes. This is obviously polynomial time. You can write it like this in polynomial time because you're just reading from left to right and writing the constraints. Then you should put them into a matrix, but that's okay. So that's an example how these things work. Quite impressive. Quite nice. So there are many more much harder things. Question 4. This is the support video for question 4.
Does this have a year? Yeah. No.
2017.
Is this 2017?
I think so, yeah. So what is the decision version of the shortest path? Straight from what's the input? Straight from the notes. A graph G, 2 vertices, U and V. Now, the optimization version wants you to find the shortest path from U to V. Okay. The decision version wants a number, rational number, so K as an extra bit of the input, and the question is, can you do better than K, or at worst K? So is there a path in G from U to V of length no more than K? That's the decision version of the shortest path problem. Clear enough?
Yeah.
Okay, traveling salesman problem, decision version. I don't remember what exactly we did in the notes. Question approximately, maybe I should check. It's in the 3 versions.
Oh, is it in this? Oh, I don't know. Oh,
Somewhere.
yeah. So this one. The other one I've got.
Maybe I've missed it. Okay, anyway, so you want, we certainly did this problem, so it's where you want to visit the customers and you want to travel the least possible distance. So that's the optimization version.
Yeah.
Now, a graph G with edge lengths. It has to have edge lengths, sorry. If you don't know how long the edges are, then you can do shortest path by just counting the edges, but that's not. Okay, so this is a distance. A distance function d, which for any pair of numbers between 0 and 1, 0 and n, 1 and n, gives you some rational number. Okay. So this, that's the set of 1, 2, n. Okay, so you have n places somewhere. Between any two of them, you know the distance or the time it takes to travel from one to the other.
Yeah.
And a rational number again. Okay, that's a decision motion. And the question is, well, the question really was, is there a talk? Can you go start in 1, okay, go around and come back to 1 and not travel more than k? Okay, so is there a permutation? I'll group theorize it. Is there a permutation? I of those such that when you add all these distances, so when you add I goes from 1 to n, the distance from first to the next, n minus 1. And then you add the distance from the last back to the first, you get no more than k. Does it make sense, or shall I explain in more depth?
Just pretty clear.
And you order them in such a way that if you travel around and come back, so this is the one for coming back, and this is from the first one to the second, and from the second to the third, and so on. And then you end into the nth one, so you have to add one from the nth one back to the first one. Extra. Can you do this and not travel more than k? So it should be a question. Okay, so we have this. What's the next question?
Give an example of a real life situation where this is a bit or a similar problem needs to be solved.
Yeah, I'm sure you can come up with one quickly.
Short path. Real life situation, like delivery truck, logistics. Trying to get from point A to B.
Travel says it's just going to be postman, isn't it?
Yeah, you could say postman.
Yeah,
yeah, delivery.
Possibly, yes. That's, so this is kind of a delivery problems.
Mm-hmm.
Or a van is delivering, wants to go back to the depot as well.
Yeah. Yeah.
For example, yes. This one, for example, sat nav.
Right.
Yeah.
I want to go from here to there.
Yeah.
That's the shortest.
Fastest, fastest, shortest path.
So that's an example. Next question. The shortest path is solvable in polynomial time, as we know. These two facts, in fact, it should be.
Will you do this on Friday? Or do we have something else to do on Friday?
I need to talk to Philip whether it's him or me.
If it's what?
Well, either I'll go through another question. Or do you want this question again?
Depends
Continue on, yeah, definitely. Continue on, definitely.
No, well, yes. So certainly we'll do some kind of revision, but I've not spoken to Philip about it. So maybe, because what we probably are going to do, because we did it last year and the year before with somebody else and so on, is that there are 2 of these labs left.
Yeah.
So I'll take one and he'll take the other.
Okay.
But I've not spoken to him whether he wants this week's lab or the one in after holiday. So I'll ask him and I'll send an announcement about it.
That'd be awesome.
Okay, the practical consequences, let's just finish it very quickly. Okay, are that for the shortest path where it comes in practice, like SatNav, your phone can do it, basically. Okay, that's the consequence. So if you want to go to Durham, just take your phone out, say Durham, yeah, and it finds the shortest path very quickly. And if you go off route, then it recalculates it very quickly as well. And so that's the efficiency of polynomial-time algorithms. Band delivery to get the optimal solution to the best way is pretty much impossible. So can't be sure.
If it is
It's the best way. So people settle for approximate solutions. So, or they will just guess. This could be it.
Well, I find that obviously, like the other hitch in the sort of program is that you could be not just traveling by foot, you could be traveling on a bike, and sometimes not bounded by the roads. So therefore, your options are limited. But you could see a path, let's say an alleyway or over a field, but they don't calculate it that way. But would that be too in depth?
Well, that's probably not a consequence of that.
Yeah, or a real life situation.
It might be a real life situation, but it's not this kind of mathematical reality that we're talking about. Yes, it's a different sort of problem. So the problem here is really that when people are doing big scheduling, especially if this is simple, but there are even harder problems. Like you have several vans and you've got too many customers to do with one van, and you have to split them several vans. Becoming even more and more complex, and these things just can't be solved efficiently with current algorithms. So if someone finds that P is equal to MP, there will be solvable. We don't know. So what they're doing is they're settling for suboptimal solutions. Or another sequence is that what Alan is doing recomputations of NTR problems for railway scheduling. You have to think of some tricks, otherwise it would take too long to calculate. Yes. Thank you very much. Stop.